Welcome to this talk on streamlining constraints. Today, specifically, we will talk about the effect of multiple models, and we will use the balanced academic curriculum problem as a demonstrator of this. This is joint work with Patrick, Nguyen, and Ian. We are all from the School of Computer Science at the University of St. Andrews. I'll start by defining what streamlining is. Say you are trying to solve instances of a problem class and you have developed a correct model for this problem class. But this model doesn't quite have the performance that you're after. One way of improving the performance of a model like this would be adding constraints, adding implied constraints, and to allow better propagation inside the solver. Implied constraints can be generated manually by studying the constraints of a model, or automatically. There are a few methods of doing this automatically. In either case, implied constraints will be sound, so they will follow from a base model, and they will not be allowed to remove any solutions. Streamlining constraints are very similar to implied constraints. However, they can be much more aggressive because they don't have to be sound. They are allowed to remove some solutions, but not all. So they will need to retain at least one solution. This is very useful for a CSP where we are looking for a single solution. Not quite useful when we need to enumerate all solutions for a CSP. Previous work on this topic by myself and co-authors was on the generation of candidate streamlining constraints for a given problem specification written in Essence, and an automated selection method using a Monte Carlo search on the model lattice that is defined by these candidate streamliners. Today, I'd like to talk about allowing Conjure to generate multiple models, because previous work that was published in CP 2019 didn't really take full advantage of Conjure. Conjure is able to generate alternative models for a given Essence problem spec, whereas previous work only used the default model using the default heuristics of Conjure. One thing to notice here is that streamlining constraints are added to a problem specification, hence they change the input. So under different streamlining constraints, you will have a different set of models in the output. Different models will perform differently, and the hypothesis we will test here is whether we will be able to find models that work better for a certain set of streamlining constraints in comparison to others. The source of different models inside of Conjure basically comes from two places. First one is using different viewpoints for the high-level abstract decision variables in Essence, and the second one is different ways of encoding problem constraints. I would like to give an overview of the whole process here, because I won't be able to go into detail of these points. But hopefully this overview will be enough of a teaser, and you will go and read the paper where you will find all the details. The input of the process is a problem specification written for a problem class in the language Essence. The output will be a portfolio of streamlined models, so they won't be Essence problem specifications, they will be models in the Essence Prime language. Each model is identified by a set of streamlining constraints and a bunch of modeling choices. So each member of the portfolio will not simply be a base model plus a bunch of streamlining constraints. They can use entirely different viewpoints, entirely different ways of writing, refining constraints in them. A portfolio on its own isn't very useful, because when you are presented with an unseen instance, you need to have a way of choosing a member of this portfolio and to apply that on that instance. For this purpose, we will use basically an off-the-shelf tool for us called Autofolio, and we will train Autofolio at the same time as we do our Monte Carlo tree search on the model lattice. The components of the system are: one, a way of generating training instances, and we have another paper from CP last year where we describe how we go about generating training instances. You don't have to use that method. You could have a generator for that problem class that you write by hand, or you could have a bunch of training instances already generated for you or collected from a real-world dataset. The second component is a way of generating candidate streamlining constraints, and this is done by Conjur for us. And the third component is a multi-objective MCTS. This is used for selecting a set of streamlining constraints that work well. Here, the objectives are a wide applicability of the selected streamlining constraints on the training instances, and when they're applicable, a large reduction. If we want to achieve a large reduction in the amount of search we do for as wide ranges of instances as possible. Since we have multiple models to consider for each specific set of streamlining constraints, we will use racing methods to choose between models, and all the details of this will be in the paper. The BACP problem. The core of the BACP problem is to find a mapping bit from courses to periods. So for every course, we need to find a period for that course to happen. And there are a bunch of problem constraints to satisfy here. First one is to do with prerequisites. The second and the third ones are to do with spreading the load to periods. I will quickly jump to our results. So BACP was indeed one of the problems that we had in our previous work. In our previous work, where we only considered a single default model, that is the first row here, we had 25 test instances, and using a virtual best solver analysis, so where we take the best member of our portfolio, we saw that on 92% of the instances we saw an improvement, and when we saw an improvement, the improvement was 95%. So we reduced the search by 95%. We only spent 5% of the time that was required by the original model. This is a huge reduction. However, on top of that, here, when we allow Conjur to use multiple models in the second row, both the percentage of places where we can apply, where we can get an improvement increases from 92% to 96%, and in those cases, in those 96%, we get a larger reduction. The search is reduced to almost 1% of the original search. Of course, this is the virtual best solver setup, which is not really achievable. You need an oracle to achieve this. We then see autofolio results, which is what happened in real life, and we used autofolio to choose which member of the portfolio to use. And here, using multiple models, we see an improvement as well. The overall reduction on these instances goes down slightly, but the applicability goes from 72% to 92% of the test instances. I'd like to quickly show you the sources of models in the portfolio. The resulting portfolio has models in it which come from different levels of heuristics in Conjur. I didn't have time to describe these levels in this talk. However, if you look at the paper, you will see the details of these. And what is significant here is that the portfolio isn't dominated by models that come from a single level. We have models that come from different levels, different kinds of heuristics in Conjur, and they are all useful members of the portfolio. In summary, we show in this paper that exploring alternative models helps. These models seem to have complementary performance. For different test instances, we see different models performing better than others. This new architecture, this new way of doing things overall is better than always using the default model given by Conjur, which is of course the default model for a reason. We thought that was a good choice, good sort of general choice, but allowing it to explore different models helps. And there are a lot of details in the paper, and I'd like to invite you to read the paper if you're interested. Thank you very much for listening.